Thanks, Rick. Well, thank you very much. I'm delighted to be here and grateful for the honor of giving the Templeton Lecture at CU this year. In his biography of the famous philosopher Ludwig Wittgenstein, Norman Malcolm reports, Wittgenstein said that he sometimes had a certain experience which could best be described by saying that when I have it, I wonder at the existence of the world. I am then inclined to use such phrases as, how extraordinary that anything should exist, or how extraordinary that the world should exist. This mystery, which according to Aristotle lay at the very root of philosophy, is one which thoughtful persons cannot avoid. Derek Parfit, a contemporary philosopher, for example, agrees no question is more sublime than why there is a universe, why there is anything rather than nothing. This question led the great German polymath Gottfried Wilhelm Leibniz to posit the existence of a necessary being, which carries within itself the sufficient reason for its existence, and which constitutes the sufficient reason for the existence of everything else in the world. Leibniz identified this being as God. Naturalists, on the other hand, have typically claimed that the space-time universe itself is necessary in its existence. That is to say, eternal, uncaused, incorruptible, and indestructible. Thus, David Hume, for example, queried, why may not the material universe be the necessarily existent being? Indeed, how can anything that exists from eternity have a cause, since that relation implies a priority in time and a beginning of existence? There's no warrant for going beyond the universe to posit a supernatural ground of its existence. As Bertrand Russell put it so succinctly in his BBC radio debate with Frederick Copleston, the universe is just there, and that's all. It was thus the presumed eternality of the universe that allowed naturalistic minds to rest comfortably in the face of the mystery of existence. This feeling of equanimity was first disturbed when in 1917 Albert Einstein made a cosmological application of his newly discovered gravitational theory, the general theory of relativity. In so doing, he assumed that the universe is homogeneous and isotropic, and that it exists in a steady state, with a constant mean mass density and a constant curvature of space. To his chagrin, however, he found that general relativity would not permit such a model of the universe, unless he introduced into his gravitational field equations a certain fudge factor, lambda, in order to counterbalance the gravitational effect of matter, and so ensure a static universe. But Einstein's universe was balanced on a razor's edge, and the least perturbation, even the transport of matter from one part of the universe to another, would upset the balance and cause the universe either to implode or to expand. By taking this feature of Einstein's model seriously, the Russian mathematician Alexander Friedmann and the Belgian astronomer Georges Lemaitre were able to formulate independently in the 1920s solutions to the field equations which predicted an expanding universe. In 1929, the American astronomer Edwin Hubble showed that the red shift in the optical spectra of light from distant galaxies was a common feature of all measured galaxies and was proportional to their distance from us. This redshift, first observed by Vesto Slipher in 1926, was taken to be a Doppler effect indicative of the recessional motion of the light sources in the line of sight. Incredibly, what Hubble had discovered was the expansion of the universe predicted by Friedmann and Lemaitre on the basis of Einstein's general theory of relativity. It was a veritable turning point in the history of science. Of all the great predictions that science has ever made over the centuries, exclaims physicist John Wheeler, was there ever one greater than this, to predict, and predict correctly, and predict against all expectation, a phenomenon so fantastic as the expansion of the universe. According to the Friedmann-Lemaitre model, as time proceeds, the distances separating galaxies become greater. It's important to understand that as a theory based in the general theory of relativity, the model does not describe the expansion of the material content of the universe into a pre-existing, empty Newtonian space, but rather the expansion of space itself. The ideal particles of the cosmological fluid, which is constituted by the matter and energy of the universe, are actually conceived to be at rest with respect to space, but to recede progressively from one another as space itself expands or stretches, just as buttons glued to the surface of a balloon would recede from one another as the balloon is inflated. As the universe expands, it becomes less and less dense. This has the astonishing implication that as one reverses the expansion and extrapolates back in time, the universe becomes progressively denser until one arrives at a state of infinite density at some point in the finite past. This state represents a singularity at which space-time curvature, along with temperature, pressure, and density, becomes infinite. It therefore constitutes an edge or boundary to space-time itself. P.C.W. Davies, a British physicist, comments, if we extrapolate this prediction to its extreme, we reach a point when all distances in the universe have shrunk to zero. An initial cosmological singularity therefore forms a past temporal extremity to the universe. We cannot continue physical reasoning or even the concept of space-time through such an extremity. For this reason, most cosmologists think of the initial singularity as the beginning of the universe. On this view, the Big Bang represents the creation event, the creation not only of all the matter and energy in the universe, but also of space-time itself. The term Big Bang, originally a derisive expression coined by Fred Hoyle to characterize the beginning of the universe predicted by the Friedmann-Lemaitre model, is thus potentially misleading, since the expansion cannot be visualized from the outside, there being no outside, just as there is no before with respect to the Big Bang. The standard Big Bang model, as the Friedmann-Lemaitre model came to be called, thus describes a universe which is not eternal in the past, but which came into being a finite time ago. Moreover, and this deserves underscoring, the origin it posits is an absolute origin ex nihilo, that is, out of nothing. For not only all matter and energy, but space and time themselves come into being at the initial cosmological singularity. As Barrow and Tipler emphasize, at the singularity, space and time came into existence. Literally nothing existed before the singularity. So if the universe originated at such a singularity, we would truly have a creation ex nihilo. Thus, we may graphically represent space-time as a cone. Space and time begin to exist at the initial cosmological singularity. On such a model, the universe originates ex nihilo in the sense that at the initial cosmological singularity, it is true that there is no earlier space-time point, or it is false that something existed prior to the singularity. Now, such a conclusion is profoundly disturbing for anyone who ponders it, for the question cannot be suppressed. Why does the universe exist instead of just nothing? Sir Arthur Eddington, contemplating the beginning of the universe, opined that the expansion of the universe was so preposterous and incredible that, quote, "I feel almost an indignation that anyone should believe in it, except myself." He finally felt forced to conclude the beginning seems to present insuperable difficulties unless we agree to look on it as frankly supernatural. Standard Big Bang cosmogony thus presents a challenge to metaphysical naturalism, since, in the words of Quentin Smith, it belongs analytically to the concept of the cosmological singularity that it is not the effect of prior physical events. The definition of a singularity entails that it is impossible to extend the space-time manifold beyond the singularity. This rules out the idea that the singularity is an effect of some prior natural process, end quote. Smith recognizes that the question which then remains is whether the Big Bang might not be plausibly regarded as the result of a supernatural cause. Otherwise, one must say that the universe simply sprang into being, uncaused, out of absolutely nothing. Thus, in the words of one astrophysical team, the problem of the origin involves a certain metaphysical aspect which may be either appealing or revolting. Revolted by these stark metaphysical alternatives presented by an absolute beginning of the universe, naturalists have been understandably eager to subvert the standard model and restore an eternal universe. In 1948, Fred Hoyle, together with Herman Bondi and Thomas Gold, broached the first alternative to the standard Big Bang theory, the steady state model of the origin of the universe. According to this theory, the universe is in a state of isotropic cosmic expansion, but as the galaxies recede from one another, new matter is drawn into being ex nihilo in the interstices of space created by the galactic recession. The expansion of the universe in the steady state model can be compared to a rubber sheet with buttons glued to it. As the sheet is stretched and the buttons separate, new buttons come into being in the voids created by the recession of the previously existing buttons. Thus, the condition of the sheet remains constant over time, and no beginning of the process need be posited. If one extrapolates the expansion of the universe back in time, the density of the universe never increases, because the matter and energy simply vanish as the galaxies mutually approach. The steady-state theory never secured a single piece of experimental verification. Its appeal was purely metaphysical. The discovery of progressively more radio galaxies at ever greater distances undermined the theory by showing that in the past the universe was significantly different than it is today, thus contradicting the notion of a steady state of the universe. Instead, it became increasingly evident that the universe had an evolutionary history. But the decisive refutation of the steady-state model came with two discoveries which constituted, in addition to the galactic redshift, the most significant evidence for the Big Bang theory, namely the cosmogonic nucleosynthesis of the light elements and the microwave background radiation. With respect to the first, although the heavy elements were synthesized in the stellar furnaces, stellar nucleosynthesis could not manufacture the abundant light elements, such as helium and deuterium. These could only have been created in the extreme conditions present in the first moment of the Big Bang. With respect to the second, In 1965, a serendipitous discovery revealed the existence of a cosmic background radiation predicted in 1946 by George Gamow on the basis of the Standard Model. This radiation, now shifted into the microwave region of the spectrum, consists of photons emitted during a very hot and dense phase of the universe. In the minds of almost all cosmologists, the cosmic background radiation therefore decisively discredited the steady-state theory. Now, the Standard Model was based on the assumptions of homogeneity and isotropy. In the 1960s and 70s, some cosmologists suggested that by denying homogeneity and isotropy in the universe, one might be able to craft an oscillating model of the universe and thus avert the absolute beginning predicted by the Standard Model. If the internal gravitational pull of the mass of the universe were able to overcome the force of the expansion, then the expansion could be reversed into a cosmic contraction, a sort of cosmic big crunch. Now, if the universe were not homogeneous and isotropic, then the collapsing universe might not coalesce at a point, but the material contents of the universe might pass one another by. So the universe would appear to bounce back from the contraction into a new expansion phase. If this process could be repeated indefinitely, then the beginning of the universe might be avoided. And thus, on the oscillating model of the universe, we see that the universe is sort of like a concertina, expanding and contracting from eternity. Now, such a theory is extraordinarily speculative, but again, there were metaphysical motivations for adopting this model. The prospects of the oscillating universe were severely dimmed in 1970, however, by Roger Penrose and Stephen Hawking's formulation of the singularity theorems which bear their names. The theorems disclose that under very generalized conditions, an initial cosmological singularity is inevitable, even for inhomogeneous and non-isotropic universes. Reflecting on the impact of this discovery, Hawking notes that the Hawking-Penrose singularity theorems, and I quote, led to the abandonment of attempts, mainly by the Russians, to argue that there was a previous contracting phase and a non-singular bounce into expansion. Instead, he says, almost everyone now believes that the universe and time itself had a beginning at the Big Bang, end quote. Despite the fact that no space-time trajectory can be extended through a singularity, the oscillating model nevertheless exhibited a stubborn persistence. But 3 further strikes were lodged against it. Summarizing, first, there are no known physics which would cause a collapsing universe to bounce back to a new expansion. Secondly, the observational evidence indicated that the mean mass density of the universe was simply insufficient to generate enough gravitational attraction to halt and reverse the expansion. Indeed, the most recent discovery suggests that the expansion is actually accelerating rather than decelerating. And thirdly, the thermodynamic properties of an oscillating model turned out to imply the very beginning of the universe that its proponents sought to avoid. Looking back, quantum cosmologist Christopher Isham muses, perhaps the best argument in favor of the thesis that the Big Bang supports theism is the obvious unease with which it is greeted by some atheist physicists. At times, this has led to scientific ideas such as continuous creation, that is the steady-state theory, or an oscillating universe being advanced with a tenacity which so exceeds their intrinsic worth that one can only suspect the operation of psychological forces lying very much deeper than the usual academic desire of a theorist to support his or her theory. The oscillating model drew its life from its avoidance of an absolute beginning of the universe. But once other models became available claiming to offer the same benefit, the oscillating model sank into oblivion under the weight of its own deficiencies. Now, it was realized that a physical description of the universe prior to the Planck time, that is 10 to the negative 43 second after the Big Bang singularity, would require the introduction of quantum physics in addition to general relativity. On the quantum level, so-called virtual particles are thought to arise due to fluctuations in the energy locked up in the vacuum. Particles which the Heisenberg indeterminacy principle allows to exist for a fleeting moment before dissolving back into the vacuum. In 1973, Edward Tryon speculated whether the universe might not be a long-lived virtual particle whose total energy is zero, born out of the primordial vacuum. This seemingly bizarre speculation gave rise to a new generation of cosmogonic theories, which we may call vacuum fluctuation models. These models were closely related to an adjustment to the standard model known as inflation. In an attempt to explain, or explain away, depending on one's viewpoint, the astonishing large-scale homogeneity and isotropy of the universe, certain theorists proposed that between 10 to the negative 35 and 10 to the negative 33 second after the Big Bang singularity, the universe underwent a phase of super rapid or inflationary expansion, which served to push the inhomogeneities out beyond our event horizon. Prior to the inflationary era, the universe was merely empty space, or a vacuum. And the material universe was born when the vacuum energy was converted into matter via a quantum mechanical phase transition. Now, in most inflationary models, as one extrapolates backward in time, beyond the Planck time, the universe continues to shrink down toward the initial singularity. But in vacuum fluctuation models, it is hypothesized that prior to inflation, the universe as a whole was not, in fact, expanding. Rather, the universe as a whole is a primordial vacuum which exists eternally in a steady state. And throughout this vacuum, subatomic fluctuations occur by means of which matter is created and many universes are born. Our expanding universe is just one of these many universes, an indefinite number of which are conceived in the womb of this greater mother universe as a whole. And thus the beginning of our universe does not represent an absolute beginning, but merely a change in the eternal, uncaused universe as a whole. Though still bandied about in the popular press, vacuum fluctuation models did not outlive the decade of the 1980s. Not only were there theoretical problems with the production mechanisms of matter, but these models faced a deep internal incoherence. According to such models, it is impossible to specify precisely when and where a fluctuation will occur in the primordial vacuum, which will then grow into a universe. Within any finite interval of time, there is a positive probability of such a fluctuation occurring at any point in space. Thus, given infinite past time, universes will be eventually spawned at every point in the primordial vacuum. And as they expand, they will begin to collide with one another and coalesce with one another. Thus, given infinite past time, we should now be observing an infinitely old universe, not a relatively young one. Isham, who is probably Britain's leading quantum cosmologist, has called this problem and I quote, fairly lethal to vacuum fluctuation models, and says that therefore they did not find wide acceptance. About the only way to avert the problem would be to postulate an expansion of the primordial vacuum itself. But then we're right back to the absolute origin implied by the Standard Model. According to Isham, these models were therefore jettisoned 20 years ago, and he says nothing much has been done with them since. Inflation also forms the context for the next alternative that we'll consider, the chaotic inflationary model. One of the most fertile of the inflation theorists has been the Russian cosmologist Andrei Linde, who currently champions his chaotic inflationary model. According to cosmologist Robert Brandenberger, Linde's chaotic inflation scenario is the only viable inflationary model in the sense that it is not plagued with internal inconsistencies, as old inflation and new inflation models are. In Linde's model, inflation never ends. Each inflating domain of the universe, when it reaches a certain volume, gives rise via inflation to another domain, and so on ad infinitum. Linde's model thus has an infinite future. But Linde is troubled at the prospect of an absolute beginning. He writes, "The most difficult aspect of this problem is not the existence of the singularity itself, but the question of what was before the singularity. This problem," he says, "lies somewhere at the boundary between physics and metaphysics." Linde therefore proposes that chaotic inflation is not only endless, but beginningless. Every domain in the universe is the product of inflation in another prior domain, so that the singularity is averted, and with it as well the question of what came before, or more accurately, I think, what caused it. In 1994, however, Arvind Borde and Alexander Willam showed that a universe eternally inflating toward the future cannot be geodesically complete in the past. That is to say, there must have existed at some point in the indefinite past an initial singularity. They write, "A model in which the inflationary phase has no end naturally leads to this question. Can this model also be extended to the infinite past, avoiding in this way the problem of the initial singularity?" They answer, "This is in fact not possible in future eternal inflationary spacetimes, as long as they obey some reasonable physical conditions. Such models must necessarily possess initial singularities." They conclude, "The fact that inflationary spacetimes are past incomplete forces one to address the question of what, if anything, came before." In his response to Borde and Willam's article, Linde concurs with their conclusions. He says there must have been a Big Bang singularity at some point in the past. At the close of their analysis of Linde's chaotic inflationary model, Borde and Willam say, with respect to Linde's metaphysical question, the most promising way to deal with this problem is probably to treat the universe quantum mechanically and describe it by a wave function rather than by a classical space-time. They thereby allude to the next class of models which we'll discuss, namely quantum gravity models. Willam and more famously James Hartle and Stephen Hawking have proposed models of the universe which Willam candidly calls exercises in metaphysical cosmology. In his best-selling popularization of his theory, Hawking even reveals an explicitly theological orientation. He concedes that on the Standard Model, one could legitimately identify the Big Bang singularity as the instant at which God created the universe. Indeed, He thinks that a number of attempts to avoid the Big Bang were probably motivated by the feeling that a beginning of time smacks of divine intervention. He sees his own model as preferable to the Standard Model because there would be no edge of space-time at which one would have to appeal to God or some new law. As we shall see, he is not at all reluctant to draw theological conclusions on the basis of his model. Both the Hartle-Hawking and the Vilenkin models eliminate the initial singularity by transforming the conical hypersurface of classical spacetime into a smooth, curved hypersurface having no edge. This is accomplished by the introduction of imaginary numbers, that is to say multiples of the square root of -1 for the time variable in Einstein's gravitational equations, which effectively eliminates the singularity. Hawking sees profound theological implications in the model. I quote, "The idea that space and time may form a closed surface without boundary has profound implications for the role of God in the affairs of the universe. So long as the universe had a beginning, we could suppose it had a creator. But if the universe is really completely self-contained, having no boundary or edge, it would have neither beginning nor end. What place, then, for a creator?" Hawking does not deny the existence of God, but he does think that his model eliminates the need for a creator of the universe. Now, the key to assessing this theological claim is the physical interpretation of quantum gravity models. By positing a finite imaginary time on a closed geometrical surface prior to the Planck time, rather than an infinite time on an open geometrical surface, these models actually seem to support, rather than undercut, the idea that time had a beginning. Such theories, if successful, enable us to model the beginning of the universe without an initial singularity, involving infinite density, temperature, pressure, and so on. As Barrow points out, this type of quantum universe has not always existed. It comes into being, just as the classical cosmologies could. But it does not start at a Big Bang where physical quantities are infinite. Barrow points out that such models are often described as giving a picture of creation out of nothing. The only caveat being that in this case there is no definite point of creation. Hartle-Hawking themselves construe their model as giving, quote, "the amplitude for the universe to appear from nothing," end quote. And Hawking has asserted that according to the model, the universe, quote, "would be quite literally created out of nothing, not just out of the vacuum, but out of absolutely nothing at all, because there is nothing outside the universe," end quote. Similarly, Vilenkin claims that his model describes the creation of the universe, quote, "from literally nothing," end quote. Taken at face value, these statements entail the beginning of the universe. Hence, Hawking evidently means to include himself when he asserts, "Today, virtually everybody believes that the universe and time itself had a beginning at the Big Bang." Hawking's theological statement, quoted a moment ago, on the theological implications of his model, must therefore be understood to mean that on such models, there are no beginning and ending points. But having a beginning does not entail having a beginning point. Even in the Standard Model, theorists sometimes cut out the initial singular point without thinking that, therefore, the space-time no longer begins to exist. And the problem of the origin of the universe would be thereby neatly solved. Time begins to exist just in case for any finite temporal interval there are only a finite number of equal temporal intervals earlier than it. That condition is fulfilled for quantum gravity models as well as for the Standard Model. Thus, quantum gravity models, like the Standard Model, imply the beginning of the universe. Perhaps it will be said that such an interpretation of quantum gravity models fails to take seriously the idea of imaginary time. Introducing imaginary numbers for the time variable in Einstein's equation has the peculiar effect of making the time dimension indistinguishable from space. But in that case, the imaginary time regime prior to the Planck time is not truly a space-time at all, but rather a Euclidean four-dimensional space. Construed realistically, such a four-space would be evacuated of all temporal becoming and would simply exist timelessly. Thus, Willam characterizes this regime as a state in which all our basic notions of space, time, energy, entropy, etc. lose their meaning. Hawking describes it as completely self-contained and not affected by anything outside itself. It would be neither created nor destroyed. It would just be. The question which arises for this construal of the model is whether such an interpretation is meant to be taken realistically or merely instrumentally. On this score, there can be little doubt that the use of imaginary quantities for time is a mere mathematical device without ontological significance. For first of all, there is no intelligible physical interpretation of imaginary time on offer. What, for example, would it mean to speak of the lapse of an imaginary second, or of a physical object enduring through 2 imaginary minutes? Secondly, time is metaphysically distinct from space. Its moments are ordered by an earlier than relation, which does not similarly order points in space. But this essential difference between time and space is obscured by imaginary time. Therefore, imaginary time is most plausibly construed as simply a mathematical auxiliary device to grease the equations and get to realistic answers. Significantly, the use of imaginary quantities for time is an inherent feature of all quantum gravity models. This precludes their being construed realistically as accounts of the origins of space-time in a timelessly existing four-space. Rather, they are simply ways of modeling the real beginning of the universe ex nihilo in such a way as to not involve a singularity. What brought the universe into being remains unexplained on such accounts. So whether its origin was at a singular point or not, the fact remains that the universe began to exist, and this is a prediction of any realistic interpretation of quantum gravity models. We finally come to the extreme edge of cosmological speculation, string cosmology. These models are based on an alternative to the standard quark model of elementary particle physics. So-called string theory, or M theory, conceives of the fundamental building blocks of matter to be not particles like quarks, but tiny vibrating strings of energy. Now, string theory is so complicated and embryonic in its development that all its equations have not yet even been stated, much less solved. But that has not deterred some cosmologists from trying to craft cosmological models based on concepts of string theory to try to avert the beginning predicted by the standard Big Bang cosmology. The most celebrated of these scenarios in the popular press has been the so-called ekpyrotic scenario championed by Paul Steinhardt. In the most recent revision, the cyclic ekpyrotic model, we're asked to envision 2 three-dimensional membranes or brains for short, existing in a 5-dimensional hyperspace. One of these branes is our universe. These two branes are said to be in an eternal cycle in which they approach each other, collide, and then rebound again. And it is the collision of the other brane with our brane that causes our universe to expand. With each collision, the expansion is renewed. And thus these branes exist in an eternal cycle of approach and retreat, ever renewing the expansion of our universe. So even though our 3-dimensional universe is expanding, it never had a beginning. Now, apart from its almost entirely speculative nature, the ekpyrotic scenario is plagued with problems. For example, the Horava-Witten version of string theory on which the scenario is based predicts that the brane on which we live have a positive tension. But in the ekpyrotic scenario, it has a negative tension in contradiction to the theory. Attempts to rectify this so far have not been successful. Second, the model requires an extraordinary amount of ad hoc fine-tuning. For example, the two branes have to be so perfectly aligned with one another that even at a distance of 10 to the 30th power greater than the space between them, they cannot deviate from parallel by more than 10 to the negative 60th power. There's no explanation at all for this extraordinary setup. Third, the collapsing and retreating branes are the equivalent of a 4-dimensional universe which undergoes an eternal cycle of contractions and expansions. In this sense, the cyclic ekpyrotic model is just our old friend, the oscillating model, writ large in 5 dimensions. As such, it faces exactly the same problem as the original. There is no way for the universe to pass through a singularity at the end of each cycle to begin a new cycle, and no physics to cause a non-singular bounce. Finally, even if the branes could bounce back, there is no means of the physical information in one cycle being carried through to the next cycle, so that the ekpyrotic scenario has been unable to deliver on its promises to explain the large-scale structure of the observable universe. These are just some of the problems afflicting the model. It's no wonder that Andre Linde has recently complained that while the cyclic ekpyrotic scenario is very popular among journalists, it has remained rather unpopular among scientists. But let all that pass. Perhaps all these problems can somehow be solved. The more important point is that it turns out that, like the chaotic inflationary model, the cyclic ekpyrotic scenario cannot be eternal in the past. In September of 2001, Bord and Vilenkin, in cooperation with Alan Guth, were able to generalize their earlier results on inflationary models in such a way as to extend their conclusion to other models. Specifically, they note, our argument can be straightforwardly extended to cosmology in higher dimensions, specifically brane cosmology. According to Vilenkin, it follows from our theorem that the cyclic universe is past incomplete. That is to say, the need for an initial cosmological singularity has not been eliminated, and therefore such a universe cannot be past eternal. With each successive failure of alternative cosmogonic theories to avoid the absolute beginning of the universe predicted by the Standard Model, that prediction has been confirmed. The beginning of the universe, of space and time themselves, reveals the contingency of the universe. The universe is not evidently necessarily existent, as Hume suggested, since it is not eternal, and therefore its existence does cry out for explanation. It is no longer sufficient to dismiss this problem with a shrug and a slogan. The universe is just there, and that's all. Of course, In view of the metaphysical issues raised by the prospect of a beginning of the universe, we may be confident that the quest to avert such a beginning will continue unabated. Such efforts are to be encouraged, and we have no reason to think that such attempts at falsification of this prediction will result in anything other than further corroboration of the prediction of a beginning. In the meantime, the beginning cannot be wished away. Given its origin ex nihilo, the demand why the universe exists rather than nothing presses insistently upon us. The discovery that the universe is not eternal but had a beginning implies that the universe is not necessary in its existence, and therefore has its ground in a transcendent being. The only way of avoiding this conclusion would be to deny Leibniz's conviction that whatever exists has a reason for its existence, either in the necessity of its own nature or else in an external ground, and to claim that the universe simply sprang into being, uncaused, out of nothing. Reflecting upon the current situation, P.C.W. Davies muses, what caused the Big Bang? One might consider some supernatural force, some agency beyond space and time as being responsible for the Big Bang. Or one might prefer to regard the Big Bang as an event without a cause. It seems to me that we don't have too much choice, either something outside of the physical world or an event without a cause. End quote. But suppose we go the route of postulating some causal agency beyond space and time as being responsible for the origin of the universe. A conceptual analysis of what properties must be possessed by such an ultra-mundane cause enables us to recover a striking number of the traditional divine attributes. For as the cause of space and time, this entity must transcend space and time, and therefore exist atemporally and non-spatially, at least sans the universe. This transcendent cause must therefore be changeless and immaterial, since timelessness entails changelessness, and changelessness implies immateriality. Such a cause must be beginningless and uncaused, at least in the sense of lacking any antecedent causal conditions. Occam's razor will shave away further causes, since we should not multiply causes beyond necessity. This entity must, moreover, be unimaginably powerful, since it created the universe out of nothing. Finally, and most strikingly, such a transcendent cause is plausibly to be regarded as personal. As Richard Swinburne points out, there are two types of causal explanation: scientific explanations in terms of laws and initial conditions, and personal explanations in terms of agents and their volitions. A first state of the universe cannot have a scientific explanation, since there is nothing before it, and therefore it can be accounted for only in terms of a personal explanation. Moreover, the personhood of the cause of the universe is implied by its timelessness and immateriality, since the only entities we know of which can possess such properties are either minds or abstract objects. And abstract objects, like numbers and relations and properties, do not stand in causal relations. Therefore, the transcendent cause of the origin of the universe must be of the order of mind. This same conclusion is also implied by the origin of a temporal effect from a timeless cause. For if the cause of the universe were an impersonal set of necessary and sufficient conditions, it could not exist without its effect. Otherwise, it wouldn't be truly sufficient for the effect. The only way for the cause to be timeless and changeless, but for its effect to originate de novo a finite time ago, is for the cause to be a personal agent who freely chooses to bring about an effect in time without any antecedent determining conditions. And thus we are brought not merely to a transcendent cause of the universe, but to its personal creator. We can summarize the argument this evening as follows. Number one, whatever exists has a reason for its existence, either in the necessity of its own nature or else in an external ground. Two, whatever begins to exist is not necessary in its existence. Three, if the universe has an external ground of its existence, then there exists a personal creator of the universe who, sans the universe, is timeless, spaceless, beginningless, changeless, necessary, uncaused, and enormously powerful. 4, the universe began to exist. 5, therefore the universe is not necessary in its existence. That follows from step 2 and step 4. Whatever begins to exist is not necessary in its existence. The universe began to exist, therefore the universe is not necessary in its existence. 6, therefore the universe has an external ground of its existence. That follows from 1 and 5. Whatever exists has a reason for its existence, either in the necessity of its own nature or in an external ground. The universe is not necessary in its existence, therefore the universe has an external ground of its existence. And finally, 7, therefore there exists a personal creator of the universe who, sans the universe, is timeless, spaceless, beginningless, changeless, necessary, uncaused, and enormously powerful. And this, as Thomas Aquinas was wont to remark, is what everybody means by God.